Thank you. Thank you very much. Does it work? Can you hear me? Great. So thank you for inviting me. This is a fantastic workshop. I've been learning a lot. In this talk, you won't have flapping wings, this kind of applied stuff. You will have some electrostatics, though, a little bit. So I'll speak about eigenvalues of random matrices and some connected, purely complex analysis objects. Okay, let me first motivate the problem. You have a selection of n by n hermitian matrices, right? You have a big box with these matrices, and we'll be pulling out matrices randomly. You have to establish the law that you use to select your random matrices, and the law, probability law we'll be using, has this form. So it's exponential, so it's a weight function times just kind of a plain Lebesgue weight on the entries of the random matrix, and this is a weight that makes all this integral finite, and the weight looks like this. It's a trace of a polynomial of a matrix, right? We take a polynomial typically of even degree. For instance, the classical Gaussian case is just x squared or x squared over 2, and it's also pre-multiplied by the size of the matrix, okay? And this is normalizing constant to have this, the whole integral equal to 1. So this is the rule, which means that the smaller the trace is, the higher probability you get your matrix. And the questions, network questions in this field is, what are the eigenvalues? And these are, what are the expected eigenvalues? What are the distribution of the spectrum? Or, equivalently, because you know that all eigenvalues are real in this case, what is the expected characteristic polynomial of these matrices, right? Okay, so we will be interested, my interest is always in the asymptotic theory. So when the size of the matrix grows large, we can model actually some physical phenomena, and I want to describe the asymptotic distribution of these eigenvalues, or equivalently of these polynomials, the asymptotic property of these polynomials. Let me start with explaining what happens in this case. Oh, by the way, it's called unitary ensemble because it's unitarily invariant, right? If you conjugate all the matrices unitarily, nothing changes. The law is still the same, so that's why it's called unitary ensemble. So this is the data. We have this probability law. We are looking at this polynomial equivalently eigenvalues, and the answer in the limit is well known. It's classical already because the first property of these polynomials is they're orthogonal. Orthogonal with respect to this weight on the real line. Well, the weight, it's a varying weight, right? It's rescaled, so it depends on the degree of the polynomial, but it's an orthogonal polynomial. So immediately, you can use the analytic theory of orthogonal polynomials to predict what will happen with this. So in the case, think that when x was, where the polynomial v was x squared, you have like Hermite polynomials. Again, rescaled, but you know what to do. But in general, you have the following answer. You look, so you want to keep track of the eigenvalues, the number of them grows. So you want to describe the global picture. What you do for that, you introduce the zero counting measure. So you put a weight 1 over n at each point, n points in total, so it's a unit measure. And you just wonder, does this sequence of zero counting measures have a limit? So if you have a limit, it kind of describes asymptotically, globally, how these zeros or eigenvalues distribute, right? So there is a description of this limiting measure in this case, and it's so-called the equilibrium measure. So what it means is that among all the unit measures, because remember, each guy here was a unit measure, the limit is still a unit measure. So among all the possible unit measures, pick the one that minimizes this functional. This is the energy functional. The first sum accounts for the energy, internal energy of this particle, like repelling each other. Plus you have the so-called external field given by the polynomial that you had here upstairs that modifies the whole electrostatic background. You minimize the energy, and this is the equilibrium measure, right? Minimal energy, equilibrium. And this is, the equilibrium measure is exactly the guy that you expect to have here. That's a unique, it's uniquely defined by this property. And also another property that also characterizes this equilibrium measure is that if you look at the Cauchy transform, by the way, it's a very nice trick. So you're looking at measures. These are real analysis objects. This is Lebesgue theory. I work in complex analysis, so I want to drag it to my playground. So instead of looking at the measure, I look at its Cauchy transform, which is analytic at least outside of the support of the measure, right? It's a nice holomorphic function. Now, if you look at the Cauchy transform of this measure, the equilibrium measure, it's in fact solves a quadratic equation. So it's algebraic function, okay? It's also characterizes this measure. So the answer in this case is simple. Well, I'm not saying that determining exactly this equilibrium measure, it still requires some work, although this part, having an algebraic function, algebraic equation for the Cauchy transform, helps a lot, because then you can recover the Cauchy transform, and once you know the Cauchy transform, the so-called Sakotsky-Plemel, I think Ken mentioned this theorem, allows you to recover the measure itself. You're done. Okay, this the. Sorry? The star. Oh, the star here or the star here?
No, right below.
Oh, sorry, plane. Yeah. So this thing I mentioned, it's well defined, easily defined outside of the support of the measure, right? When z is sitting outside, you're not integrating, so you don't have any singularity there. But in general, it still makes sense almost everywhere with respect to the plane Lebesgue measure on the plane. So it's correctly defined function almost everywhere on the plane. Thank you. Sorry. Okay. So for instance, I mentioned, if you have x squared, you have just a Hermite polynomial. You just take from a book how a Hermite polynomial behave, and you have the whole answer. For instance, you know that this equilibrium measure with external field x squared is the so-called circular semicircle law. So the distribution it has a maximum of 0 and decays all the way up to square root of 2. And also the Cauchy transform of this measure solves this simple quadratic equation from where you can actually recover this measure very easily. Okay, that's classic already. So I will be looking at a little bit more complicated object, which is the Hermitian plus external source. So now my probability distribution is modified a little bit. You still have the polynomial, a certain polynomial of a matrix sitting in the weight, but also you have this term. It's a fixed matrix, A. You have a certain emission matrix that is called external source, and it's multiplying your matrix M, and this is my probability distribution now. So I change the way I select my matrices from my box of Hermitian matrices. Now, this is no longer unitary invariant, obviously. So everything becomes much more complicated, but richer and also very interesting. So again, we'll be looking at the asymptotic behavior. So what happens with the eigenvalues or with the expected characteristic polynomial in this model. And I will be looking at very specific case, well studied, but already has a lot of interesting features, when my matrix has only 2 eigenvalues. Well, this matrix is Hermitian, so can be diagonalized. So without loss of generality, you can just assume that your matrix is diagonal. And imagine it has one eigenvalue with multiplicity n1, and another with multiplicity n2. Again, with the shift, you can symmetrize, so no loss of generality. You can assume that the matrix looks like A repeated n1 times, and minus negative A n2 times. And the question is, we go to infinity. We send the total size of the matrix to infinity, but obviously now you have 2 parameters, n1 and 2. You have to decide how you send them to infinity. Assume we go along certain ray. They proportionally grow, right? And so that will be another parameter in my problem now. What is the proportion of the dimension of eigenvalue A and eigenvalue negative A, okay? So my talk basically is about connection of these four objects. So first of all, this thing we already have seen before. If we look at the eigenvalue counting measure or the zero counting measure of these polynomials, what is the possible limit? The second thing is there any algebraic equation that is solved by the Cauchy transform of this limit? Then, remember, I spoke about minimizing certain energy. Is there any analog for this electrostatic problem? In this case, it will be no longer necessarily a minimum, but a saddle point of certain energy functional. And finally, it's also very interesting in this theory to know what kind of universal behavior, kind of different behaviors you can get, for instance, the endpoints of the support of the measure and so on, right? So these four objects, and what is known, for instance, a lot of people worked here, many of them even here. Well, for a no, as I said, A is non-existent, then nothing to do. It's a classical. In the case of symmetric, totally symmetric case, so imagine you have an even polynomial and also the proportion of eigenvalues A and minus A are exactly the same, and there have been results by Apteker, Blecher, Euler, McLaughlin, Ken is here, and Zinjastan. Another case that's been studied, and Tom also, if I'm not mistaken, has studied this case. It's a called small rank perturbation, when one of the eigenvalues is kept fixed, and the rest, obviously, the other eigenvalue goes to infinity. And that's another situation being studied. And finally, in the x square over 2, in the Gaussian case, a lot is known, because many things here can actually work out explicitly. And for instance, the traces work, and if I'm not mistaken about this Pearcey behavior, it's also here. So I'm sorry if I'm not mentioning everybody, but okay, let's move on. So what we did recently with my co-author, with Guilherme Silva, in 2016 we studied this connection. So we basically proved that if you have certain type of saddle points of the energy, then necessarily you have an algebraic equation connected to it. That's one connection being already kind of established. Then, more recently, we studied these connections, the saddle points with the universality classes, and as I said, the algebraic equation also gives you saddle points. And finally, we're finishing now the proof that the limits, possible limits of these zero counting measures necessarily are given by these two problems. So the talk is about this connection. I just wanted to give a scheme of the talk, and so let's concentrate first and on this part. So I'm looking at possible limits of these zero counting measures. Can I associate a certain equation to this algebraic equation? So remember, the input we have diagonal matrix A of this form, n1 and n2 are multiplicities, and we look at this guy. The first difference with the classical case that this polynomial is no longer orthogonal. It satisfies so-called multiple orthogonality. In this case, it's a multiple orthogonal polynomial of type 2, which means the polynomial has kind of distributed its orthogonality between two weights, or two measures. So part of the orthogonality condition from 0 to k1 minus 1 is with respect to the measure given by the weight v minus ax, and the rest of the conditions correspond to v plus ax. This is multiple orthogonal polynomials. I'm trying to advocate the role of these multiple orthogonal polynomials because, well, they were introduced and they were studied, I would say, in the 80s, for instance, from a point of view approximation theory. Also in the number theory, they have some applications. But it looked like they only were restricted to that area. Now, in random matrices, they appear quite naturally. It turns out their very rich and sophisticated analytic theory has direct application in all this studies. So the first thing, as I said, multiple orthogonal polynomials. Then we have the following theorem. Fortunately, because of the weights are so nice, exponential functions, these are entire functions, we can derive a differential equation that relates, that connects with the polynomials. And it looks like this. So let's take a vector. Essentially, you take your polynomial, this guy, oh, by the way, I had to say, the polynomial looking at, it's embedded, since you have now two indices, n1 and 2, instead of having just a sequence of polynomials, you have the whole table of polynomials, right? And this guy, it's embedded. It's one polynomial of degree n1 and 2. But if you look at its neighbors, like n1 and 2 minus 1 or n1 minus 1 and 2, put them in a vector and multiply by this weight, let's call it a wave function, then this wave function satisfies a matrix-valued differential equation. So the way it's proved, by the way, or I'll mention it in a second now. So another thing we prove connected is that when, so remember this is the polynomial, so we denote its coefficients by v sub k, and we have the following equation. So if we look at the characteristic equation of the matrix R that took part in the ODE, the characteristic equation, it's a cubic equation because, well, it was 3 by 3 matrix after all. But we have certain conditions on the coefficient. This condition is totally determined. The condition P1 is the less determined because we only know the bound on its degree. M is the degree of this polynomial, right? And finally, this polynomial, we know its first couple of coefficients and nothing else, where the alpha n is the proportion enters in this coefficient, and a was the eigenvalue. So we know this. And then we say the following. If the zeros of these polynomials are uniformly bounded on the real line, then we have that this determinant, if we look at this determinant, so who is here? Instead of taking arbitrary variable xi, we take this variable xi, which is this expression. So if we look here, we see this is just the Cauchy transform of my zero counting measure of this guy. So we put like a weight 1 over n at the 0, integrate with respect to this measure, minus this v prime. Okay? So it says, it doesn't say it's equal to 0, but it tends to 0 when n goes to infinity. So from here, it's a kind of a finite dimensional theorem. We won't make n go to 0, this right side go to 0, and we will have the conclusion we're looking for. Okay, the proof of this, as I said, we use obviously Riemann-Hilbert formalization of our orthogonality. This is the great thing. So already several people, and during the day, so many people will mention Riemann-Hilbert. The fantastic thing is we have much more complicated orthogonality. We have now multiple orthogonality, but still we can characterize the polynomials using Riemann-Hilbert problem that was mentioned by Ken, except now it will be 3 by 3 problem and not 2 by 2, like for instance we saw yesterday, but it still works. So the good thing about this problem is that we can make a transformation, simple transformation of the original. We take this vector, we put it in the matrix, and we can make a simple transformation of this problem in order to get constant jumps. Now, if you have a typical problem like boundary values from the left equals boundary value from the right times a constant matrix, you can differentiate both sides, and the constant matrix doesn't change. It's still there. So if you multiply, and then you can cancel this constant jumps just using inverse of one matrix times the other, and essentially you get this. So that there is a matrix R. You still don't know nothing about it, but you know that the matrix is entire, has no jumps, such that connects the derivative of ut and the t itself. Now, the way you determine this r, essentially, if it's entire, it's totally determined by its behavior at infinity, right? So the coefficients then are given by behavior at infinity. You know a priori from the original Riemann-Hilbert problem, you know the behavior at infinity, you can determine this. Now, you need still to compute this matrix to have something meaningful. And the good thing, there is another sequence of functions, in this case, that are bi-orthogonal with the polynomials using these functions. And they are written in terms of Cauchy transforms. You can give everything explicit. And finally, get your matrix R. Now, this matrix can equivalently be expressed in terms of the coefficients of the recurrence relation. Because it turns out that the polynomial, remember classical standard theory of orthogonal polynomials, they have like 3 terms recurrence relation associated. Now it's multiple orthogonality. You have a longer recurrence relation, but it's still there. The bi-orthogonal also satisfy the same recurrence relation, and using some transformation, you can express this guy in terms of coefficients. So the key assumption is that if zeros are uniformly bound in the real line, all the coefficients in this matrix R are uniformly bounded. And then you can take limit converging sequences. This is, by the way, if and only if. In this case, you can prove coefficients uniformly bounded means 0 uniformly bounded, but vice versa. So the assumption we pose on the zeros can be equivalent to the coefficients of the recurrence relations are all bounded. Okay, so that's the idea of this part. So as I said, our goal was to make it go to infinity. So with the assumption we had, I still keep this assumption that if zeros are uniformly bounded, then pick any limit, because now you have limits. Pick any limit, and then this limit will satisfy, its Cauchy transform will satisfy this cubic equation, where the polynomial, as I said, P1, the only thing to have 3 parameters. It is bounded, the degree bounded by m minus 2. And in the case of this coefficient, you also have 3 coefficients in general, but you know the first 2 of them. Okay? So this is the first connection that says any limit, any expected limit of the eigenvalues, in this sense, is associated to this cubic equation. Yeah, so I just wanted to insist that C, and this is, oh, by the way, it's not the Cauchy transform, but the Cauchy transform minus the derivative of the polynomial that solves this equation. So it means that we will consider these equations in general like the central object the next step. So imagine now we have equation, cubic equation, that has this form with all the same constraints. I just copy and paste. By the way, we dropped the assumption m has to be of even degree. It could even be of odd degree, although it's not directly associated to matrix random model, but still it works. And the only assumption we put that could look a little bit artificial is one of the solutions of this cubic equation can be written in form as a combination of v prime and the Cauchy transform a certain unit measure. Now we see it's not artificial because actually that's what happens with the actual limits of the eigenvalues, but we call a spectral curve any cubic equation that has these properties. So the next step is essentially say, okay, we have a cubic equation of this form, we have a spectral curve. What kind of electrostatic problem can we associate with this cubic equation?
But when you split the kind of the free term into 2 polynomials, maybe 3 is missed.
Yeah. Oh, no. It's missing here. Yeah, the first typo, sorry. It's obviously here because that copy and paste. This is not the free term. This is a linear term, okay? Sorry, thank you. Okay. Well, so now we will concentrate on this part. So we have algebraic equation, and we want to connect to the certain settled point problem in potential theory. And by the way, mention this universality classes we obtain. So, as I said, logarithmic potential theory is the key tool when you study polynomials on the plane. And I will define the mutual energy of two distributions by this convolution, double convolution with the logarithmic kernel. Okay? And also, we will be studying vector-valued problems. So this is another difference with the classical case when we had a single measure that described everything. Now we have to introduce a vector-valued problem with three components. It's a little bit, a few years ago, looked unexpected. Now it's clear that apparently it's the right setting to study this kind of problems. So imagine you have a measure made of three components. I try to paint them in red, blue, and orange just to keep track of what's going on. And the total energy of the system is given by this functional, this combination. So we identify here several components made of this mutual energies. So first of all, the three guys is just the internal energy of each component. Then we have a certain combination of mutual energies of each component. We have three players. And finally, we have the external field. Now, if you look here, we have plus and minus. It essentially tells you that from this set of three measures, mu1 and mu2 are mutually repelling. Mu2 and mu3 are also mutually repelling, but mu1 and mu3 are attracting each other. Right? So we have this complicated configuration of three measures, or if you want, charges, with three different signs or colors. And here, the external field is given. Basically, the first two guys you already have seen before, V plus AX, V minus AX. The third one, just for compatibility, is the difference of these two, so it's 2AX. So this is the functional we'll be trying to minimize. But the problem is, now we have to allow, because this measure, in general, can be on the complex plane. And we have to allow a complex plane to be a conductor. Not as before, we had the measure living on the real line. Only the real line was a conductor. Everything was like insulator. Now the complex plane is conductor. You no longer expect to have a global minimum of this energy. The energy can only have settle points. So it has like a local maximum in one direction, a local minimum in another direction. So we'll be looking for the settle points of this kind of functional. We have to put some constraints on the measure. And this is another difference with the classical case. I cannot tell you what is total mass of mu1, mu2, mu3. Instead of that, I give some kind of linear relations. I know that mu1 plus mu2 is 1, and mu1 minus mu3 is alpha. Alpha, remember, is the parameter that tells me in which direction we are moving, what is the ray. And just to give you a hint why this condition, because at the end, my conclusion will be that in these three components, mu1 plus mu2 give me exactly my asymptotic distribution of eigenvalues, which is total mass 1. Remember, it's a limit is the unit measure. So I want to look at this that looks complicated problem and find the eigenvalues. Find the critical, the settle points. What is a settle point? I'm not writing in detail the equations because it's a little bit. But the idea is the following. You take your plane with your measures living on the plane, and you make a certain variation of the plane, just as like a shift of the plane given by certain analytic functions and a parameter t, complex parameter t. And you compare your original energy with the energy of the shifted world. If this energy in the first derivative of this shift is 0, that's what you call the settle point of the energy. Okay? Well, the definition is not very helpful to calculate, but it allows to connect with the cubic equations I mentioned before. And that was something that we proved partially in the previous paper, partially in the recent one, that says the following. So if you have a spectral curve, remember, spectral curve is a cubic equation with a set of conditions on them. If we have a spectral curve, then there exists always a vector measure of this form that I mentioned with the following properties. The first two guys live on the real line. Mu1 and mu2, they are supporting the real line. And as I said, the sum of these two measures, they together will give me this asymptotic distribution of the eigenvalues, of the zeros of the average characteristic polynomial. Mu3 could be 0 or not. But if it's not 0, then it will be supported on a certain arc in the complex plane. And it's a connected arc, symmetric with respect to the real line. And finally, I want to look at the points where the density of this guy vanish. Obviously not where it's totally identically 0, but some point where the density vanish. Could be the endpoints or some point in the interior. It turns out that there are only 3 possibilities, basically. One is we call classical case, where everything behaves essentially like a square root, decaying like square root, for instance, or multiples of that. The second behavior is so-called Pearcey type behavior, where it's essentially you get exactly cubic root of at this point. And finally, a little bit unexpected, I haven't seen this behavior before, 5/3. We don't have any other behavior regardless, so it's total generality. We don't assume anything about the polynomial v, and also about alpha, no symmetry at all. We have only the 3 behaviors, which is interesting, at least for people working in this area. But that's kind of an outcome of this analysis. As I said, this a priori, it's not even connected to the random matrix model. V could be of odd degree, which is not related to a random matrix, but still it works the same. Yep.
Could you show the variation problem?
Yeah, the variation problem is... Yeah, E is this guy. So as I said, we have, well... Oh, the no, what I'm saying is the following. So this is the problem. You give me a spectral curve, and then I will find a measure of 3 components such that this energy, this is a perfectly defined energy regardless of spectral. Well, what I take from the spectral curve is the definition of V's, right? V1, V2. You gave me the spectral curve. V is the coefficient in the spectral curve, right? And so when you gave me a spectral curve, you gave me V, you gave me A, and you gave me alpha. And I assure you that there's a triple of measures that gives me the settle point. And the Cauchy transform plus or minus V prime solve, yeah, that's right. Okay. Okay, so just to illustrate this is an actual calculation, although it was done by Guilherme, by my co-author. So we took the case where everything is known, the quartic case. We have this polynomial. It's a symmetric quartic polynomial. Alpha we took symmetric, 1/2. Everything is proportional. And just we make A go from 0 to 1. So when A is very close to 0, basically what is happening is the following. Colors here are not totally clear, but this is the measure mu1. This is a component mu1. It's sitting on the real line. This is a component mu3, and component mu2 is gone. No mu2 there. As A starts growing, so they start separating the eigenvalues, what is happening is this. So it's invaded. Let me stop it here. So the support of the measure mu3 invaded the support of mu1, and now it's split and measured mu1 and mu2. So these 2 measures together still describe the asymptotics of the eigenvalues. Mu3, the support is shrinking, and now is invading also, intersecting with these 2 measures. Now we keep going, so A is still continues increasing until a certain moment where the mu3 disappears. And after that, what is happening, we only have mu1 and mu2. After that, what is happening, that these 2 guys start separating. Right? Mu3, it's already disappeared from the map, and but still together they describe the whole. This is kind of a typical dynamics we can see when we move these parameters. Okay, some ideas. As I said, we start from this equation. That's essentially the only a priori information we have with the properties of P1 and P0 that I mentioned before, from where you can read off your polynomial V, at least a derivative, and the coefficients alpha and A. So first of all, you look at this cubic equation, and you say it has 3 solutions. And you can easily, since you had assumed that was essential, that one of the solutions looked like a v prime plus the Cauchy transform, it means that one of the solutions, let's call it psi1, looks like this. V prime plus something started at 1 over z. Once you have this, the other two solutions are kind of immediate. They're asymptotic distribution at infinity, just playing with the properties of the solution of a cubic equation. Okay? Now, the next thing you do, because still when you have a quadratic equation, you can write everything explicitly. With a cubic equation, you no longer expect to write it. You use this Cardano formula, which is extremely inconvenient in many cases. Instead of that, what you do, you just go to the Riemann surface, where we really feel comfortable working with the cubic equation. So remember, we have now a 3-sheeted Riemann surface. And let's assume we numerate the sheets in such a way that my solution psi1 lives on the sheet number 1, the psi2 on the 2, and the 3 on the 3. And that's what we assume. And now we create something that it's an extremely useful tool. That's another favorite toy of mine. It's so-called quadratic differential. So what we do is the following. We take on the sheet number 1, we take a look at the difference of the solution 2 and 3. So the solution that don't belong to the sheet number 1, square it, take minus, multiply by dz squared. And you keep doing it on every the other two sheets. What is beautiful about that is that when you put this thing together, it turns out to be something globally correctly defined on the Riemann surface. So now you have an object which is correctly defined the whole Riemann surface, and we have to look at so-called trajectories of these quadratic differentials. Now let's look at this more carefully. The trajectories of the quadratic differential we can define here in a simple way. They just level lines of this integral. So we take like a square root of the quadratic differential. We take its primitive, and we'll look where the real part keeps constant, right? So obviously, when you say about square root, it can be like plus and minus, since you're just tracing, you're following where the real part of the primitive is constant. You don't care which sign you're using. So there are certain curves. In fact, they give a foliation of the whole Riemann surface. But you will be looking at certain specific curves from there. The components of the vector critical measure, in fact, that's another thing you have to prove, live on these curves. That's, again, not trivial, because remember, the only thing you know about the critical measure is it makes certain functional, the first derivative equal to 0. You have no further information about that. Turns out they necessarily have to live on curves. And these curves are given by equation of the form real part of this integral equal to constant. Okay? But remember, so you have to trace to follow these curves along the whole Riemann surface. So when the curve goes to the next sheet, you have to continue that and just keep track of it until it gets back. It can be quite complicated geometry, but you can do stuff with that. Now, some of these trajectories, in fact, work as the perfect branch cuts. Remember, you have Riemann surface. You can cut it in such a way that it's separated in sheets. It's kind of a free, but they are structured in such a way that they make the perfect cuts. And the key ingredient of the whole analysis is just to study these trajectories. What is their global geometry? How they behave? What is the existent and non-existent trajectory connecting two concrete points, and so on. This is a nice complex analysis exercise. So the key fact that we proved from where everything follows is that you only have two possibilities. You look at your quadratic differential, it's everything symmetric, so only look at the upper half plane, and look at the first sheet. Turns out that the structure is such that it has only two possibilities. Either no 0 in the upper half plane, or only 1, 0. And depending if no 0 and 1, 0, we call it unsaturated regime or saturated regime, just borrowing the terminology from some previous works. So let me just show what's going on. In the non-saturated, unsaturated regime, essentially what you have is what are painted in blue and red are parts of trajectory connecting the branch points of the Riemann surface. And as you see, they're just following the real line. They are made in such a way that the blue trajectories connect the sheet number 1, number 3, and the red connect number 1 and number 2. They can intersect, sometimes they can collide, and only at one single point. That's why you have only very specific type of universality behavior at this single point. But that is what's happening when it's non-saturated. Nothing else, no other zero is sitting here in the upper half plane. Now, if you go to the saturated regime where 0 appeared, then, then what happens, you have another cut, branch cut. Now you have zeros here and here. You have another branch cut that will make for the support of your measure mu3. This is the guy here that now connects the sheets 2 and 3. Again, they can collide, and some point it happened that all three come together. You saw already in the picture when this situation happens. The only two configurations possible. Okay, let me connect it finally with some previous work, because obviously this is not the first electrostatic model that's been described for such kind of random matrix model.
Andrei,
Yep.
can you go back to the previous picture and just remind us which measures repel and which measures?
Oh, yeah, right. Oh, these guys repel each other. So red and red repel each other, right? And the measure mu1, so red and orange, they attract. Okay? But remember, it's a complex, so they attract but still repelled by the other. So the whole interaction, guessing it just from the fact that these two guys repel each other, but the mu3 and mu2 attract, mu1 attract, it's not trivial. Okay? Yeah, as I said, I want to make some short comment on the previous work. So in this work, in 2011, Bleher, Delvaux, Coilers, they introduced an electrostatic model that was for a very specific case, totally symmetric case, where the polynomial is even and alpha is 1/2. So we have the same number of eigenvalues a and minus a. So in this case, they introduced the following model. They have only two components, electrostatic model of two components, where they know a priori what is the size of each component. Nu1 is of size 1, and Nu2 is of size 1/2. The next thing you know that Nu1 lives on the real line. Nu2 lives on the vertical axis, imaginary axis. So here, as I said, the measure of size 1, here the measure of the size 1/2. They also have so-called upper constraint. So you only look at measures on this imaginary axis. They are strictly less or equal. The density is strictly less or equal than a over pi. A is your eigenvalue. It means that when a is close to the axis, it's really a strong constraint. When a is far away, then it's almost a non-existent constraint. But you have this upper constraint for this component over here. And you look at the following electrostatic model. Now, again, you have Nu1 and Nu2, these components. You have the energy of each component, internal energy. But Nu1 and Nu2 are attracting each other. That's why this guy, the mutual energy, appears with a negative sign. And you have an external field, given very similar to what we had before. V, we had V minus AX, V plus AX. Here it's V minus A absolute value of X. Now, they take this matrix, these energies with all these constraints, and then among all of them, they minimize the energy. And they show that the minimizer exists. Not only that, that this Nu1 component actually describes the asymptotics of the eigenvalues. So it was absolutely natural to ask ourselves, what about us? So we have another model, in this case of three components. How does it work in this situation? So in this case, we have the following result. Well, first of all, when we find the solution to our model, all three components can be present. But what is definitely happens is that mu2 and mu3 will be living on the left-hand half plane, necessarily. Mu1 lives on the right half plane. The second thing, the sum of mu1 and mu2 turns out to be equal to mu1, as it should be. Then that's why we're, well, happy, because no contradiction. Because in our theorem, remember, mu1 plus mu2 described asymptotics. In their model, mu1 described asymptotics, so it matches. And finally, how you produce this measure mu2 from our model mu2, mu1, mu2, mu3, the answer is in terms of potential theory. What you have to do, take mu2 and mu3 and make the balayage onto the vertical line. What is the balayage? It's essentially a logarithmic potential theory term that says you can create a new measure on the vertical line such that from the right-hand side, the potential of the new measure looks exactly the same as the potential of the original measure. So you move these measures on the vertical line and without changing your potential. You balayage them out. Well, it turns out that this guy, it's exactly the balayage of the components 2 and 3 on the vertical axis. What is the advantage of the model of the 3 components? Because unfortunately, the model with the constraints, because you could say, well, it has 2 components, it's easier. But the constraints has no continuation to non-symmetric case. As soon as you lose the symmetry, this 2-component model no longer works. Okay? But the 3 components is absolutely general and free. Okay, so let me finish the, even behind schedule, so you will appreciate that. So what we did is the following. The original motivation was this model that has all these components here. So you have a probability distribution of the set of random Hermitian matrices with the external field, where external field is given by a matrix with only 2 eigenvalues with a certain proportion n1 and 2, and you make everything go to infinity, the size of the matrices, all the proportions, in such a way that this proportion has a limit, alpha. So the main parameters of the problem then, it's your potential v that is appearing here, and also the proportion alpha, and obviously the position of a and negative a. So what we proved is the following. Along subsequences, you can always find the spectral curve. So it's a cubic equation that will be solved in particular by a combination of the Cauchy transform of your asymptotic distribution eigenvalues and the potential v, actually v prime. Unfortunately, and this I have to insist, that this is only assuming that the zeros of these polynomials are uniformly bounded.
How you check it?
Hmm?
How you check it?
That's a, no, that's a conditional theorem at this point. Now, for v equal x squared, this is always true. So if your potential is just Gaussian, then they are always uniformly bounded. So we think that this is a general, you don't have to put it as assumption. It's always true. But it's definitely what has to be proved. Now, so far, everybody, I have asked all the authorities, they say, yeah, it should be true, but so far, nobody has, including us, we haven't figured out yet how to prove it, although...
Before in other words, before calculating kind of the fine limits of the zeros, you have to know some rough fact about them.
It's a boundedness, yes, absolutely. Otherwise, well, otherwise we cannot take limits. We could try to play with extended complex plane and assume that still there is something, but...
So what our authorities say is that it is still true for any v, or it is a conditional v?
No, that's what no, we think that it's true for any v.
Yeah,
We only can prove it for x squared,
yeah,
okay? That's the thing. But we think that for any v is true, okay? That's why I'm saying it's kind of a conditional theorem yet. And once we have the cubic equation, the next step was establishing that immediately you can associate a measure of 3 components that is critical, and such that it will live on trajectory a certain specific quadratic differential that's built out of this equation. And you can actually calculate, as you've seen, you can actually calculate the trajectories, numerically, for instance. And the first two components will give you the asymptotic distribution of the eigenvalues of the zeros of the sequence of polynomials I mentioned before.
Please also remind how you, so I gave you V, how you define P1, P0?
No, these are free parameters. In a case x squared, everything is defined. It's just a simple calculation. So, as I said, you write the differential equation from the Riemann-Hilbert formulation. You have a certain matrix R where some parameters, it depends on the limits, right? You don't know, right?
Is it true that when you define a differential omega and you take a square root, right, because you look at the trajectories, the periods must be purely imaginary, and that will define the parameters?
No, not necessarily. So right now we're saying the following. If you're just caring about the eigenvalue distribution, then the periods has to be purely imaginary because we're expecting. In the case of random matrix models, yes. But what I'm saying is just disconnect for a second from this model. What I'm saying is any cubic equation this form, we can find the triplet of these measures that give a saddle point, right? For the saddle point, you're not necessarily to have all the periods imaginary. Or if, from the point of view of potential theory, not every constant. No. You don't need every constant on every component of the measure to be equal, right? That's why the purely imaginary periods have to do with the fact that all the constants. So the equilibrium levels up all the constants. Here I'm speaking about critical points, so this is free. Now, in the case of matrix random models, this is true. And then you will have to add certain conditions that can help you, in theory, calculate all the remaining coefficients.
And also from the point of view of, say, kind of WKB point of view, which is familiar to many people. So you can also say probably that if somehow you know the asymptotic behavior of your recurrence coefficient.
Oh, yes. From there, you can.
This is exactly the characteristic polynomial of
yes.
Matrix R. So this
absolutely.
You write, kind of say, if you want to write solution of your psi,
right.
semi-classical, you just get this as this would be WKB, and all this imaginary condition would be just condition on your.
Yes, exactly. As I said, the coefficients of. Yes, coefficients of R are written explicitly in terms of this recurrence coefficients. Yeah, that's true. So I'm not saying it's impossible to determine. It just depends what is the data you give me. If you just give me V and right, okay. Sure. Thank you. Well, as I said, this when we have this, essentially we have all the ingredients. If we wanted to make the asymptotic analysis, detailed asymptotic analysis, say of this polynomial Pn, or of other parameters, random matrix model, the reproducing kernel, and so on, a correlation kernel, we use this machinery of Riemann-Hilbert analysis, which is very powerful. It's fantastic. It was yesterday we had a talk, but it requires some transformations. And if you don't know a priori what you used for this transformation, you're in trouble. The good thing about all these models that it kind of gives you the ingredients to make this transformation. I'm not saying that it's trivial immediate, but you can something to start to work with. But obviously, I'm not explaining the Riemann-Hilbert asymptotic analysis here, although it's beautiful, because that would require another talk. Okay, so I stop here.
If you referred at one point to a saddle point being a Pearcey type,
yes.
It's normally associated in my mind with three saddle points coalescing. So if you allow enough parameters, you could have unlimited greater complexity in the standard family of such coalescing points. So is that how you think of these things?
Yeah, that's right. That's why actually we expected to have more variety of different behaviors, because it looks like we have more parameters. But it turns out that everything just works by either coalescing along the real line, eventually trapping 1 0 that comes from the complex plane. Well, 2 zeros because they are symmetric, and because of this only limited geometry of the whole problem. So the crucial thing was, although we have so many parameters, there only can be 1 0 escaping from the real line. And this guy can come to a real line and be trapped between the other 2 zeros coming together, and that's the only option. That's why we have only this 3. So square root is kind of a standard where everybody sits separately. And then you have this Pearcey when your 2 guys came together. Or when they trapped another 0, they have 5/3. Nothing else can happen. It was kind of unexpected.
If you have any number of parameters.
Any number. So V can be arbitrary degree. But there is an essential assumption that it's kind of initially looks artificial, that your cubic equation has a solution of the form Cauchy transform a unit measure plus V prime, right? It turns out that it's not artificial if you look from the perspective of random matrix theory. It always should be like that, right? But it's not then arbitrary cubic equation. It's a specific subclass of cubic equations, right?
So how is spectral here connected to the structure of the Riemann surface? What is the genus and
Yeah.
branch points? You didn't even mention this, and how the three sheets are glued together and so on.
Yeah. So, well, I tried to picture that, but I thought I won't have time to discuss this. But the way that was essentially the pictures. Let me go back, although somebody mentioned it was wrong thing to do. So the branch points are given by points on the real line, and at most 2 other points that will be complex symmetric. And depending on the case, they exist or not. So in the simplest case where they don't exist, the only branch point will be real. It's a 3-sheeted Riemann surface, and they're glued together by this scheme. So some points and some cuts between pairs of points glued to the 3rd sheet, and some cuts glued to the 2nd sheet, right? That's one structure. The genus is easy to calculate. It depending on number of cuts, and you know it's 3-sheeted. You just use standard theorem. You calculate the genus.
So there is no direct connection between the spectral here and the structure of the surface.
No, sure, of course, yes. Yeah. So actually, the curve spectral curve determines uniquely the Riemann surface, and
The zeros of the spectral curve.
oh no, but yeah, but yeah, sure, I see. So the branch points you calculate as a standard way. You have a cubic equation, you have algebraic equation, and you just look at where it's 0, where the first derivative with respect to the parameter is 0, and it's a system equation. You eliminate for there, or where the discriminant of this polynomial equation is 0, right? So it's not that you look at the curve, you know, where the eigenvalues, where the branch points are, sorry. But it's a standard calculation. It's algebraic geometry. So the branch points are directly read from the curve. That's standard. So the only thing that the assumption that this curve is not arbitrary, it has specific type of solution, makes that the only 2 possibilities you have, this, number 1, and this is number 2. That's the only thing. But yeah, it's uniquely determined, definitely.
So in your classification result of the vanishing exponents, you have this 5/3, I thought, possibility in the book. Do you have an example of a fever this occurs, or is it just a theoretical possibility?
No, example is not difficult to create. It happens exactly when, so you play with this saturated case when you have start for instance from the symmetric case studied by Coilars, when it has like part which is saturated, right? And then you modify your alpha, you move your alpha in A in such a way that you basically make this point come together. So here, this point come together and coalesce at this point that also is hitting this point here. So you can numerically play with that and find an example where it works. But I don't have explicit, like say value alpha is this and A is this, But it's not difficult to create because the origin of this 5 or 3 is clear. It's because, well, these 2 points hit together at the same time, hit the 0, but nothing else.
Since we only have 1 hour for lunch,
Oh.
I suggest that further questions are referred to the walk.
Thank you. Yes.